Before continuing on with Chapter 2, we're going to jump ahead to Section 6.1 so we can introduce 4 important concepts that are going to help us thinking about vectors and matrices. This is inner product, the length, orthogonality, and the angle between vectors. So we have two vectors, u and v, in Rn. We regard these sometimes as n by 1 matrices. We often think about a vector as a matrix with n rows and 1 column. We learned what the transpose was in the last section, so the transpose UT is a 1 by n matrix, and then the matrix product U transpose V would be a 1 by 1 matrix. And we're going to think about a 1 by 1 matrix as just a real number, a scalar. So the number U transpose V is sometimes called the inner product or the dot product of U and V, and it is written as U dot V. So here's the actual definition. We have two vectors U and V in Rn with n entries each. Then the inner product of U and V is U dot V equals U transpose V. Those are the same things. We're going to write U as a 1 by n matrix. And we have V as an n by 1 matrix, and we said that if matrix multiplication is going to work out, these have to be the same. And what we're left with is a 1 by 1 matrix, or just a scalar. And in this case, we're going to take the first entries, multiply them together, then the second entries and multiply them together, and so on and so forth, till the n entries and multiply them together. And we've seen this kind of thing when we do matrix multiplication. We take a row times a column in the exact same way. So let's do an example. Let's let U be 1, negative 2, V 2, negative 5. These are vectors in R2. And we're going to find 4 different dot products. The first one, U dot V. Remember, this means U transpose V. So we take U, we take its transpose. The column becomes a row. 1, negative 2 times 2, negative 5 would be 1 times 2 plus negative 2 times negative 5 would be 2 plus 10 is 12. Do the same thing. This time we're going to do V dot U, the different order. V transpose U. This time we're going to take V and take the transpose, and this would give us 2 times 1 plus negative 5 times negative 2, and we get the same answer out. And it is always the case that U transpose V is the same thing as V transpose U. The only thing different is the order that you're multiplying, but it doesn't make a difference because multiplication is commutative with the real numbers. Now let's look at if we take a vector and we dot product it with itself. So U dot U, or U transpose U, we're going to take U and take its transpose, and we'd have 1 times 1 plus negative 2 times negative 2. In this case, this would be 5. Let's do the same thing with V. This time we would have 2 times 2 plus negative 5 times negative 5, which would be 29. Now note another way to write this when we're thinking about a vector dot product with itself is we could take the entries of the vector and square them and then add them together. That's really what we're doing here. We just wrote it in a different way. 2 squared plus negative 5 squared here would give us what we want. And note that if we're going to be squaring entries, these have to be non-negative, greater than or equal to 0. Whenever you square a number, it has to be greater than or equal to 0. So if we're adding those numbers together, that's always greater than or equal to 0. So a vector dot product with itself is always greater than or equal to 0. So when we think about a vector dot product with itself, we're going to give a special name to that. That's going to be called the length, or the norm, or at least it's related to that. If we square root that value we just found, so the square root of V dot V, we can do, because V dot V is non-negative, which we just discussed. You can't take the square root of a negative number, but we're not going to have to worry about that. And if we take that value, the square root of that value, This is what we're going to call the length or the norm of the vector, which is denoted with the two vertical bars on each side of the vector. And this is going to be the square root of the sum of the square of the entries. And note that if we have the norm of v squared, that's just the same thing as v dot v. So another way to write v dot v, which is v transpose v, is now the norm of v squared. So let's look at our example again. We have u and v, the same vectors as before. We're going to find the norm of u, the norm of v, and we're also going to find the norm of the 0 vector. So the norm of u is that 1 squared plus negative 2 squared. This time we're going to take the square root. This will be the square root of 5. And this is the length of the vector u. And it is really the length, how you want the length to be. If we drew the vector u, we took a ruler to it, it would have a length of square root of 5 units. For v, this would be the square root of 29. And then note for 0, we have the dot product of 0 times 0 and square root. That's just the sum of 0 squared. That's 0. And it is true that if the norm of a vector is 0, this means this is if and only if the vector itself has to be 0. So you cannot have a norm be 0 unless it's the 0 vector that you're talking about. You can't have a length of a vector be 0 unless it's the 0 vector. So let's think about this length geometrically. We think about a vector identifying with a point. So if we have here the vector is AB in R2, and this corresponds to the point AB, but remember we're thinking about this as a vector from the origin out to that point. So this is the vector v here. And we have that the norm of v is the length of the vector in a standard notion of length, the length from the origin to that point AB. And we know how to find this by using the Pythagorean theorem. We have that the length of the x-coordinate is the absolute value of a. In this case, in this picture, a and b are negative values, but we don't care about it being negative, we just want to care about the length. So we use the absolute value. The length of the y-coordinate is the absolute value of b, and then we get that the length is the square root of the length of the absolute value squared plus the length of the absolute value squared. But note that we didn't actually need the absolute value there. We could have just written this as square root of a squared plus b squared, as shown in the picture. So another important result is that if we take a scalar and we multiply it by v, remember we talked about this geometrically. If we have a vector v and we multiply it by 2, all we're doing is just taking that vector and we're making it twice as long. And since we're thinking about length for the norm, then the length should be twice as long, and this is what this result says. The norm of c times v is going to be the length of c, or the absolute value of c, we don't want negative numbers involved with length, times the norm of v. And let's show this with a generic example. So let v be the vector ab. We're going to show that any scalar c, this result holds true. So first let's look at the vector cv, that is ca and cb, multiply each entry by c. The norm of cv is the square root of ca squared plus cb squared. If you square the entries, you get c squared a squared and c squared b squared. You can take out a c squared, and you can take that out of the square root, noting that when you take the square root of something squared, it's not just x, it is the absolute value of x. Sometimes that is ignored because we're thinking about positive numbers only, but it's important to put here. And then that gives us the result. So when we're thinking about length, we often want to think about a unit vector. That is a vector whose length is 1. Remember that when we're thinking about a vector has a direction and a length. And when we think about a unit vector, we're going to just say the length is as simple as it could be, 1, and we can just focus on the direction. That's going to be the purpose of a unit vector. To think about how to find a unit vector, given any vector v, we can find a vector which is in the same direction as v, but is scaled down so the length is just 1. And we can do that by multiplying by 1 over the length of that vector. Note that if we take the vector v, divide by its length, the length of u would be the length of v times 1 over v, because this is just a scalar that we're multiplying by, just like in the last example. And that length would be 1. Again, the purpose of a unit vector, they're very, very important and useful because a vector has two components, direction and length, and when you make the length 1, you can just then focus on the direction. So let's do an example. Let's let v be the vector 1, -2, 2, 0. Noting that we're writing the vector in this parenthetical notation, we can just as easily write it as a vector. We're going to find a unit vector in the same direction as v. It holds that property of direction, but it has a different length. So first compute the length of v, because we're going to have to divide by that number. This is the norm of v. This is the square root of v dot v. And it is the square root of the sum of the entries of v. In this case, the square root of 1 squared, -2 squared, 2 squared, and 0 squared, which would be the square root of 9, or 3. So the length of v is 3, and if we divide by v, that's going to give us our unit vector u. U is going to be v divided by the length of v, the norm of v divided by the length of v. And sorry, this shouldn't be the norm of v here. This should be just v itself divided by the norm. Would be 1/3 v. We get a scaling factor of 1/3 times that vector 1, -2, 2, 0. And we get a vector 1/3, -2/3, 2/3, 0. And we could verify that this has a length of 1. The norm of u is the sum of the squares of the entries. 1/3 squared plus -2/3 squared plus 2/3 squared plus 0 squared would give us square root of 1/9 plus 4/9 plus 4/9 plus 0, which is the square root of 9/9, which is 1. And remember here, what we're doing is we have a vector, in this case in 4-dimensional space, v, which has a length of 3, and all we're doing is keeping the direction the same. We are going to make it a unit vector, a length of 1 instead. So next we're going to think about the distance between two vectors. So if I have two vectors in Rn, the distance between u and v, which is sometimes written as dist, distance of u and v, is the length of the vector u minus v. So that is the norm of u minus v. So let's look at this in this R2 picture. We have the vector v here, which corresponds to the vector v on the other side of that parallelogram. We also have the vector minus v, which we're going to write here. So this is the vector minus v. And we have the vector u, which is the vector right here. So note that when I have u minus v, that's the same thing as u plus negative v. And if I take a head-to-tail method, if I take u and then I take negative v, I have this vector u minus v. And the length of that vector is the distance between u and v. It is this distance right here. If we wrote our vectors the normal way, it is the length of this line segment. So let's do an example. Let's compute the distance between the vectors u and v, 7, 1, and 3, 2. Well, u minus v is easy to find. It's easy to add or subtract vectors. You just do it component-wise. So 7 minus 3 is 4, 1 minus 2 is negative 1. And then to find the norm of that, we just add the sum of the squares of the entries. That is, the square root of 4 squared plus negative 1 squared is the square root of 17. That is the distance between those 2 points or those 2 vectors. So the next idea we're going to think about is the angle between 2 vectors. So here we're going to have u and v be non-zero vectors in either R2 or R3. But note that this generalizes to Rn. It's just hard to draw a picture of the angle between 2 vectors in Rn because we don't have the nice way to draw things in more than 3-dimensional space. But this is for any vectors. You can think about an angle between them. So the angle between them is associated with the inner product or the dot product that we've been focused on. And it has to do with the origin of the point. So in our picture here, we have the vector v here. And we have the vector u right here. And the angle is just going to be the angle from those 2 rays from the origin. And we're going to call that angle theta. So the formula that we're going to use here is u dot v is the norm of u times the norm of v times cosine of theta. We're going to think about where that comes from in just a little bit. And note that this does generalize to 3-dimensional space and above. It's just harder to draw those pictures. So let's see why this formula is true. First, we're going to look at this u minus v, the norm, squared, which we said that if you take the norm squared, that's the same thing as doing u minus v dot itself, or u minus v transpose times u minus v. Then we saw in the last section that if you take the sum or the difference of 2 things, you take its transpose, the transpose distributes to each of those things nicely. So that is u transpose minus v transpose times u minus v. Then we have different objects here we can distribute nicely with multiplication. That is, we're going to get u transpose times u. So that is u transpose times u times u transpose minus v, so minus u transpose v, minus v transpose u, then finally minus v transpose v, or plus v transpose v. And we said earlier that u transpose v is the same thing as v transpose u, so we could rewrite this as the norm of u squared, which is u transpose u, minus 2 u transpose v, plus the norm of v squared. We're going to use that to show this result in a second. So we're going to use a result here called the law of cosines, and it's not important in necessarily where this comes from. One way you can think about the law of cosines is it is a generalization of the Pythagorean theorem beyond just right triangles. So if you have an obtuse triangle or an acute triangle, then you can still think about something like the Pythagorean theorem, and it comes from the law of cosines. So the law of cosines states that u minus v, the norm of it squared, is the norm of u squared plus the norm of v squared minus 2 norm u norm v cosine of theta. Above, we showed that the norm of u minus v squared is equal to the norm of u squared minus 2u transpose v plus the norm of v squared. And then we have that. We have the norm of u squared and the norm of v squared on both sides. If we cancel those out, we're left with minus 2u transpose v equals negative 2 norm u norm v times cosine theta. And if we divide by the negative 2 on both sides, we're left with our result, u transpose v equals norm of u norm of v cosine of theta. And we often write these results in the form where I have cosine of theta equals u dot v minus the norms. Or more importantly, I'm trying to find the angle between 2 vectors. I need to write this as theta equals arc cosine of that product. So let's do an example here. We have u and v, our vectors we've been using this in this section. Find the angle theta between u and v. Well, to do that, I need u dot v. So let's find that first. So u dot v is u transpose v. That's going to be 1 times 2 plus negative 2 times negative 5, 12. And then we also need to find the norm of u and the norm of v. The norm of u is square root of 5. The norm of v is square root of 29. And if I put those together, the norm of u squared times the norm of v squared, that'll be the square root of 145. 5 times 29 is 145, and the square root comes along. So here we have that cosine of theta is equal to u dot v, which is 12, divided by those norms multiplied together, which is square root of 145. And if I take the arc cosine of that value, that's just some number, plug it into a calculator, that'll give you 0.0831 radians, or that's about 4.8 degrees. So these vectors are very close to each other. The angle between them is not very big. When we're thinking about angle, we're going to be thinking about orthogonality, and we can think about this as perpendicularity. Orthogonality means that the angle between the vectors is 90 degrees, or pi over 2 radians. So if I have a vector u and a vector v here, the angle is 90 degrees. Now the reason it's called orthogonal is for a lot of different reasons. We can think right now because perpendicularity is only in reference to a two-dimensional thing. But when we think about beyond that, in 3 dimensions and beyond that, we have this generalized notion of orthogonality. And we get that two vectors are orthogonal to each other if u dot v equals 0. And note that that would be that cosine of theta is u dot v over the norm of u squared, norm of v squared, norm of u, norm of v. And if u dot v is 0, then this would just be 0. So that means that theta would be arc cosine of 0, which means that theta is pi over 2, or 90 degrees. And the existence of orthogonal vectors is going to be very important for us later on in this course.